Hi students. In this lecture, I am going to discuss orbital velocity. Let us see what is it. It is the velocity with which a body, or you can say satellite, revolves around a planet. Let us see how to find the corresponding velocity. So assume that this is a planet. Its mass is m, radius is r. It is a planet. Now, a body, or you can say satellite, which is revolving around it in a circular orbit. So taking it is now orbit is circular. It is now following a circular path around that planet. This is now you can say satellite or a body. So here we have to focus when a body is following circular path, there must be a centripetal force. And you can see this planet exerting on this one gravitational force which is towards center of the planet. Okay, and this force is now providing centripetal force. So we can write here centripetal force is gravitational force that is equal to G m1 m2. If mass of satellite is m, G m1 m2 by r square. Here r means radius of the orbit, which is nothing but distance of the satellite from center of the planet, or we can say in terms of height, r equal to r plus h in terms of height. So this is r square. So this is according to Newton's universal law of gravitation. Okay. This is now providing centripetal force which is equal to mass into acceleration. Mass is m. Acceleration is v square by r. V square by r. See from this one r gets cancelled and mass gets cancelled. So v value, it is equal to root of gm by r. Okay. This is now orbital velocity. Okay. And you can see this velocity is always tangential to path. It is always tangential to path. That means what we can say is now this velocity is always normal to the line joining center of the planet and the satellite. Okay. At any instant. Getting it. And one more thing from this, what we can say is this velocity depends on mass of the planet and radius of the orbit. So this is not depending on mass of the satellite. Okay, right. Now, since we got velocity, we can find here it's a kinetic energy. So in the orbit, see kinetic energy how much? Kinetic energy equal to half m v square. So g m by r. This is now kinetic energy. And if you want to find potential energy, that is equal to minus g m1 m2 by r. Okay. And if you take sum of these two, that gives total energy, which is equal to minus g m by 2r, right? So this is now total energy of that satellite in that orbit. Okay. And see carefully, this is now negative value. So why total energy is negative means that negative indicates that it is bounded to this planet. That means it is now bounded to this planet because of that gravitational force of attraction. So whenever total energy is negative, it indicates that it is a bounded system. For example, if you remember electrons revolving around nucleus, and in that case also total energy of electron is negative. If you see first orbit minus 13.6 electron volt, right? That negative indicates electron is bounded to the attractive force of nucleus. Okay, right. So here see the important points what we have drawn. So velocity depends only on mass of the planet and radius of orbit. And we got here kinetic energy, potential energy, and total energy. Suppose if orbit is not circle, it is elliptical. Then in the place of total energy, see for total energy, while writing total energy, in the place of radius of the orbit, we are going to write it is semi-major axis, that is A. In the place of R, we are writing semi-major axis, that is A. So that is the only change when you are taking the total energy. And the kinetic means it is simply half mv square, and potential means minus g m m1 m2 by distance between them. Okay, so when it comes to total energy, we have to focus in the place of radius of the orbit. It is now semi-major axis of the elliptical orbit. Okay, let us see the important points regarding this. So it is the velocity with which a body revolves around a planet. Its direction is normal to the line joining the satellite and center of the planet. It depends on radius of the orbit and mass of the planet. It is independent of mass of the satellite. Okay. So these are the points we have discussed regarding orbital velocity. Let us see now escape velocity. Right. First understand what is it. Right. So we have seen in the previous one orbital velocity. There we got total energy is negative. Means it is a bounded, right? Minus g m by 2r, or you can say 2a. Okay, right. Let us take now. This is a planet of mass m, radius is r, right? So we want to project a body from a height h, from a height h, right? So we want to project now this with a velocity so that its total energy becomes zero. See, what do you mean by zero? It's a total energy zero means it is no more bounded to this planet. Means it is now escaping from the gravitational force of this planet. Okay. The meaning of total energy becoming zero, or we can say total energy becoming positive. Right. So condition is here. So we want to make a total energy zero. So how much velocity we have to provide? Height is h, or you can say this is separation is equal to, let us take small r, where this is equal to r plus h. Okay. Then see it is having potential energy minus g m by r. That is potential energy. Plus we are providing some kinetic energy to make total value zero. And this corresponding velocity is known as escape velocity. Okay. Then see from this what we get. So V is equal to mass gets cancelled. This is now root of 2gm by r. Okay. And just now we got expression for orbital velocity, right? So in terms of that, it is now root 2 times orbital velocity. Yes, we got orbital speed is root of gm by r. This is now root 2 times that value. Okay. So when total energy becomes zero, it is now escaping from the attractive force of this planet. And the path followed will be, it is a parabolic. If total energy is greater than zero, then it follows hyperbolic path while escaping from its gravitational field. Okay. So here what we have taken is conservation of mechanical energy. See, potential energy. Next, kinetic energy, sum of these two. We are making total value zero. See what it means. So when this is escaping from the attractive force of the planet, or let us make a diagram here. This is now that planet. For example, its attractive force is now up to certain range. Let us say this is now that at range, okay, that attractive force. So now this body has to cross that boundary, okay. So if it is just able to cross that boundary, just able to cross, okay, that means on reaching this boundary, its velocity equal to, on reaching that boundary, its velocity equal to zero. So we are taking now its velocity equal to zero just after crossing the boundary. Okay, right. And we are saying that up to this boundary, this plant has its influence. That means just crossing this, there is no gravitational potential energy because no influence means no potential energy. So just crossing, no kinetic. Just after crossing, no potential energy. Therefore, total value equal to zero. Okay. So we have taken conservation of mechanical energy. Potential plus kinetic equal to again potential zero, kinetic zero. So this is now escape velocity. So after crossing this, if it is a total edge is zero, it follows a parabolic path. If total edge is greater than zero, it follows hyperbolic path. Okay. And next, one more thing, if you want to calculate with what velocity it is now escaping after crossing boundary. After crossing the boundary, what is velocity of the body? Then again, we have to use now. See if we provide velocity greater than escape velocity. Then what happens is, while crossing the boundary, its kinetic energy is not zero. Okay. So I'm taking once again the same equation. See carefully. Minus G M1 M2 by R plus now this time it is not equal to V, it is greater than V. Okay. Na? Half mv square is equal to, okay, now this is greater than 0. How much? It is greater than 0, right? So what is now extra kinetic energy that we have given? Extra kinetic energy that we have given. That is what we have to focus. So just after crossing boundary, no potential energy. So no potential energy, right? Plus it has some kinetic energy, that is take it as a half m v dash square. Okay, half m v dash square, right? So potential energy plus kinetic energy which we have given, that is now greater than escape velocity, right? Now I am taking this v is equal to some k times escape velocity. Okay, where I am writing it where k value greater than 1. Okay, so we have given kinetic energy more than required to escape. Now the remaining calculation part. Remaining calculation part, half m. This is now k square v square minus m by r is equal to half m v dash square. Okay, I'm making calculation, remaining calculation. See, in the place of half m v square, what we can write? I'm taking, okay, from this one, or you can take directly from here only. In the place of half m v square, you can take minus g m by r. Okay, you can substitute that here. So remaining is now I'm taking k square outside half m v square. Writing now that minus g m by r. Okay, wait. I can take here. I can take here k square minus 1. Okay, k square minus 1 in the place of half m v square. I'm writing here k square minus 1 into, just a minute, what I have taken here. Half m v square is g m by, right? Okay, g m by r, that is equal to, half m v dash square. Mass gets cancelled. Remaining is now in the place of g m by r. What we can write? In the place of g m by r, it is v square by 2, right? From here, v square by 2. K square minus 1 into v square by 2. That is equal to v dash square by 2. 2 gets cancelled. Therefore, v dash, sorry, this is v dash. That implies v dash is equal to ve into root of k square minus 1, right? That is the speed with which it moves after crossing that boundary. Okay. See on the calculation part what we have done here. In the place of half m v square, I have taken g mm by r, that is a positive. So g mm by r minus 1, that is minus 1, equal to half m v dash square. So k square minus 1 into, this is nothing but in the place of g m by r, v square by 2. So v square by 2, 2 gets cancelled. So v dash equal to v into root of k square minus 1. So this is the velocity with which it moves after crossing that boundary. Okay. Right now, some important points regarding this. It is the minimum speed with which a body should be projected so that its total energy becomes zero. Or it is the minimum speed with which a body should be projected so that it is able to escape from the gravitational attraction of the planet. It is independent of angle of projection if rotation of planet is not considered. Okay. In this, we are simply writing a half mv square, okay? In which direction we are projecting is not important if rotation of planet is not considered, okay? Next, it depends on mass of the planet and independent of mass of the body. And next, total energy is zero. It follows parabolic path while escaping. Total energy positive. It follows hyperbolic path while escaping. Right? Next, see, let us solve problems based on this to get more clarity. What is the minimum energy required to launch a satellite of mass m from the surface of a planet of mass capital and radius r in a circular orbit at an altitude of 2r? Altitude means height. Okay. So he's asking now minimum energy required to launch a satellite. Okay. To launch a satellite from surface of the planet. Then see what we can do here. From surface of the planet. So here again we are using energy equation on surface of the planet. Energy initially potential energy minus Gm by R. Okay. Now we provide some kinetic energy. Okay. Plus K. This is our total energy at the time of projecting. Okay. When it enters into an orbit, its total energy is minus Gm by 2R, where R is radius of the orbit, that is equal to R plus H. Now in this case, H value given 2R, right? It is given 2R. Now substitute there, then K equal to Gm by R minus Gm by 2 into 3R, it is 6R. Okay. So here you can take Gm by R common. Gm by R common. Remaining is 1 minus 1 by 6. It is a 5 by 6. So this is the minimum energy we have to provide. Okay. Very simple one, direct one. This is 2013 mains question. Right. See next problem. A satellite is moving with a constant speed in a circular orbit about the Earth. An object of mass m is ejected from the satellite such that it just escapes from the gravitational pull of the Earth. At the time of ejection, the kinetic energy of the object is, this is asked in 2011 advance. So it is already in a circular orbit. Okay, speed is given v. Now object is ejected from satellite such that it just escapes from gravitational pull of the Earth. We have to find kinetic energy of the object. Right. See how we are going to solve this one. Since it is now in the satellite, if radius is r, its potential energy will be minus Gm by r, where m is now mass of that body, okay, which is ejected. It's a potential energy plus its a kinetic energy. It's a kinetic energy at the time of ejection. If total value is 0, it will escapes. It will escape from the gravitational attraction of the Earth. I'm repeating. This is the potential energy of the body which is ejected, plus this is the kinetic energy of that body at the time of ejection. If total is 0, it will escape from the gravitational attraction of Earth. So from this K equal to Gm by R. Okay. Now this can be taken as M into, in the place of Gm by R, it is nothing but V square, where V stands for orbital velocity. So this is the kinetic energy that required to escape from that attractive force. So answer is now half M, sorry, answer is mv square, right? Let's see next one. And this question also from 2016 mains. See what is given. A satellite is revolving in a circular orbit at a height h from Earth's surface, where h is very small compared to R, right? The minimum increase in its orbital velocity required so that the satellite could escape from Earth's gravitational field is close to. So this is very direct one, simple one. Already it is in the orbit, right? It is asking minimum increase. Increase in the sense extra, right? Extra how much? So already in the orbit means it is having orbital velocity, which is equal to root of Gm by R. And in this we are given condition R h is very small. When h is very small, this will be equal to root of Gm by capital R. Okay, root of Gm by capital R. Yeah. And we are knowing that escape velocity is equal to root of 2Gm by R. Why means because we are knowing that R equal to R plus H, but condition given H is very small compared to R. Okay. That means now this is root 2 times root 2 times the orbital velocity. So extra how much we have to provide? Extra value is now V minus V naught, that is root 2 minus 1 into orbital velocity. That is extra which we have to provide. Okay. So option is now it is fourth one, right? Root of GR. Okay. In the place of what we call Gm by R square, we have taken root GR, right? Gm by we taken as root of GR. The next one. So this question is from previous site 2013 advance. Two bodies, each of mass capital, are kept fixed with a separation 2L. A particle of mass m is projected from the midpoint of the line showing the centers perpendicular to the line. Gravitational constant is G. The correct statements are, so he is asking minimum velocity, sorry, minimum initial velocity of the mass m to escape from the gravitational field of the two bodies. Only values are different, options are separate, values different. And last one, energy of mass m remains constant. See how to get. Let us make a diagram for the given question. We can say two planets. In between, we project one body like this. Mass is same, m and m, separation given 2m. So this is m, this is m. This velocity we have to calculate. So condition is that we have to make its total energy positive, or we have to make at least 0. Okay. Then condition is half mv square. Next, potential energy because of this two minus G m1, m2 by r is l into 2 because of those two. This is equal to 0. Mass gets cancelled. So V value 2 to the 4, 4 gm by L. Okay, under root. That is now minimum speed we have to provide. Okay, next. Here, the only force acting is now gravitational force, which is conservative force. Therefore, the total energy of this object and these two planets is a constant. Okay, we have to take total energy means we have to focus the system. Therefore, total energy of the system is a constant. It is not just total energy of the particle. The actual sentence must be total energy of the system is a constant. So in that case, options are B and D, right? Okay. Options are B and D.